Welcome to cryptography session. The second algebraic structure in symmetric cryptography is a ring. Here a ring is defined as R. It is denoted with the symbol R. R is equal to the set of residues Zn. Zn. So R is equal to Zn, and there is a possibility of using two binary operations in Zn. So if any two operations are performed in Zn, then that will be called as ring. The first operation in this notation is plus. So the first operation must satisfy the 5 properties. So the 5 properties are like abelian group properties. That means closure, associative, identity, inverse, and commutative property. So we prove these 5 properties with the help of the first operation plus. Then it is called as abelian group. So all abelian groups are called as ring, and second operation must satisfy the first two properties, that means closure, associative properties. So we for the second operation is multiplication operation. So for the multiplication operation we should take the commutative property and the identity. That means identity means multiplicative identity. Multiplicative identity. So here already identity is available. If it is plus, the identity will be taken as 0. But if you want to prove ring concept, we should take the commutative property with the multiplication operation. That means second operation, and also the multiplicative identity for the second notation. So if these values are satisfied, then it is called as ring. So here example Z6 plus cross. Then this property is called as distributive property. So this is called as distributive property. Distributive property. So if any group is satisfying distributive property, means that ring is called as commutative ring. So for example, the question will be asked as prove R is equal to Z6 plus cross is a ring. So prove that R is a ring. So this is the first question. And second question, whether it satisfies a commutative ring or not. So this is the second question. So I am taking this part as two parts. So if I want to prove a ring property, so I should take closure with the first operation. So closure associative, that is also with first operation. First operation is addition. And then identity. Identity is also taken for addition. That means first property. And then inverse. Inverse is also will be taken for identity. So that means we should find out the additive inverse of these notations. And then commutative property. For this commutative property also we should take addition operation. So just write the values for Z6. So the values are 0, 1, 2, 3, 4, 5. And in this one, 2 is not a co-prime, 3 is not a co-prime, 4 is not a co-prime. So the answers are only 0, 1, 5. So you should take either 0, 1, 5 for checking these conditions, and you should do mod operations for the value. Then the answer will be retrieved as either 0, 1 or 5. So in this way we can able to satisfy these 5 properties. So if these 5 properties are satisfied, then that set Z6 with the plus cross operation is taken as ring. So if you want to prove it is a commutative ring, in addition with that we should check the distributive property. That means distributive property means there are two possible operations should be performed. So it will be written as plus operation and also multiplication operation. So A plus of B cross C will be written as A plus B cross A plus C. So we just check the answers for this one. So 0 plus 1 into 5. So this will be written as 0 plus 1. into 0 plus 5. So 0 plus 1 into 5, which is equal to 0 plus 1 into 0 plus 5. So if you take this value 0 plus 5, which is equal to 1 into 5. So the answers are 5 because it is Z6. So the answer is same. So distributive property is satisfied with the two operations. So if all the 6 properties are satisfied, then that ring is called as commutative ring. So in this way we can able to prove it. And another notation is the commutative property should be satisfied for the second operation also. That means the second operator is cross. So I want to take the value 0, 1, 5, any two values from this list, and you simplify the commutative property for this one. And if you want to do multiplicative inverse, so multiplicative inverse means A into A inverse, that should be equal to 1. So 0, there is no multiplicative inverse for 0. For 1, the multiplicative inverse is 1. Then if you take 5, so that should be 5 into A inverse mod 6, that should be equivalent to 1. So in this way, you should take the values for these notations. 5 0 is 0, no. 5 1s are 5, no. 5 2s are 10, it's not also possible. 5 3s are 15, it is also not possible. 5 4s are 20, it is not also possible. 5 5s are 25. So 25 means mod 6 means 1. So the multiplicative inverse of 1 is 1. The multiplicative inverse of 5 is 5. So only two multiplicative inverses are available. So if these are all satisfied, then this ring is called as commutative ring. So once again I explain the ring notations. So already we can able to prove this 5 properties with the first operation plus. So if these 5 properties are satisfied, it is called as abelian group. So if you want to prove ring, we just prove the abelian properties with first operation, and for the second operation we should prove the commutative property and also the multiplicative inverse property. In addition to that 5 properties, we should once again use a commutative and multiplicative identity with second operator. So these 7 properties are proved for a ring concept. Sometimes they can able to ask the commutative ring. So if any question is asked as a commutative ring, we should prove. In addition with the previous 7 properties, we should prove the 8th property as distributive property. So in this is the example for commutative ring with this notations. Field is denoted with F. So here also 2 set of binary operations are available. So what are all the commutative rings are available? All commutative rings are called as field. And here we are taking the second operation cross for satisfying the basic 5 properties. So if you go for ring, we are taking the first property and first operator for satisfying closure, associative, identity, inverse and commutative. If these 5 properties are satisfied with the first operator, then that is called as ring. If the same 5 operators are satisfied with the second operator, then that is called as field. This is the only difference between field and ring. So the first operation, except that the identity of the first operation has no inverse. So additive and multiplicative inverse should also be satisfied with the first operator and second operator. This finite fields concept will be discussed in next session. Thank you.